chapter on equilibrium. We had 3 chapters on equilibrium. This is the 3rd one. This one, like every other time we've done this, it seems like in Chem 2, we're going to have a topic that we're going to cover with more detail and mathematically, what we originally covered as a qualitative way. For example, don't have to copy any of this down. This is a little review of how we did this. In thermodynamics, we saw thermodynamics in Chem 1. We didn't call it that, and we didn't do a whole heck of a lot with it, aside from we saw this graph. You know, we saw the progress of reaction graph. We're basically having, energy versus time, and I asked you to be able to predict whether something absorbs or releases energy, call it endo or exothermic, hot or cold, spontaneous, favoring, or not. All right, that was all Chem 1. That's all we did. But that was thermodynamics. It's just that we spent about 1 day on it. Then here in Chem 2, we learned how to actually calculate changes in energy in a couple of different ways. MC delta T, reactants minus products, and eventually to the goal of predicting whether the reaction was ultimately spontaneous or not. So Chem 1, about 1 day. Chem 2, a whole chapter, doing it mathematically. Same thing's true with kinetics. Kinetics, we didn't call it kinetics in Chem 1. We called it, factors that increase the rate of a reaction. And we talked about them, heating and stirring up. We did a lab on them, stuff like that. But, concentration misspelled. But then when Chem 2, we learned the rate law expression. And we basically were able to predict mechanisms, how many times something's used in the slow step, all that stuff. So we did it mathematically. Same thing was true for equilibrium. We talked about equilibrium in Chem 1. Liquid plus energy equals vapor. We talked about it. We said, okay, if I heat it up, it's going to go more evaporation or more condensation. Actually, we spent quite a bit of time on that because the concept of the Chatelain's principle was kind of important. So we needed to know that. And so we spent a lot of time on that, more than just a day or so like we would have spent on these other topics. But again, nowhere near the 3 chapters we've been spending on Kc and Ka and Kb and Kw. And now what we're going to get is going to be Kc. Because we're going to talk about, again, something we saw in Chem 1. We saw these in Chem 1. We did these in Chem 1. We dissolved, and we had to write this back. In fact, this is the lab. The reason they're doing the ice cream lab in the back there is that we just finished this chapter in Chem 1, and that's what we did. You had to complete that equation. You had to write down AQs next to everything that dissolved and S's next to things that didn't. And you had to predict whether this guy was soluble and whether this guy produced a precipitate or not. That's what you did in Chem 1. It was qualitative. It wasn't just 1 day, but it was certainly not what we're going to do in this chapter. What are we going to do in this chapter? We're going to apply our knowledge of equilibrium to dissolving and precipitates. Why is that? Well, because I'm going to get to the actual notes yet in a little bit, but don't copy this. I can treat this like a precipitation reaction. A solute, I'm sorry, not precipitation, like an equilibrium reaction. Solute plus solvent yields solution. Just like our chemical reactions, we saw just like solid plus energy yields liquid and liquid plus energy yields vapor. Our phase changes, solutions are also an equilibrium problem. And we cheated back in Chem 1. All you looked up in Chem 1 was on that chart, and I think I have a chart here from Chem 1, where I put them all away. But you remember that chart. You probably still have it back in your old notebooks. Basically, that chart looked like this. Here's one. You just looked up on the chart, down one side and across the other, and you saw either a big S. A big S meant it was soluble. You saw an I meant it was insoluble. Or you saw some other letter, and I said just ignore them. Just pretend that they're I. Anything that's not soluble in water, it's all we cared about. Well, now, just like in all those other things, in thermodynamics, kinetics, and the first equilibriums, we're not just going to use a chart and predict whether it dissolves or not. We're actually going to be able to predict how much of it dissolves. Because every one of these guys who is slightly soluble, all those other letters on there with a P and whatever that are slightly soluble, have a K. It's not Ka, it's not Kb, it's not Kc, it's called Ksp, the solubility product constant. And that is what we're going to apply and be able to predict not just whether I get a precipitate, but at what concentration I'll get a precipitate. Not just whether this will dissolve, but how much of it in the water will dissolve. The actual mass and molarity. All right, so that's where we're going with this last equilibrium chapter. So we'll have had, by the time we're done, Kc back in the first chapter, Ka and Kb and Kw back in the last chapter, and now Ksp. But before we get to any of that, we have a little review to do. I'm going to review on concentration, and this is a review. Why? Because we haven't done this in a while, and when we have done it, I've noticed over the course of the past couple of labs, whenever we had to do a calculation, a concentration calculation, you generally didn't do it very well, or I had to re-teach it to you. Well, this is going to be part of every one of the questions. You're going to have to do a molarity. You're going to have to know dilutions. You're going to have to do all of those things to do these labs and to do these problems. Okay, molarity is going to be the first thing I want to go over with you. I'm not going to review. I did a lot. If you in Chem 1, if you remembered, we did percent solution, we did molality, we did normality. We've done a little bit of normality here when we talked about the acid-base titration. But I'm going to concentrate mainly when it comes to solubility on molarity and dilutions. So let's talk about molarity first. Molarity, as you remember, is moles of solute per liters of solution, I hope. Now, I'm going to give you 3 ways you're going to be calculating this throughout the course of these problems. And so I'm going to do 3 of these problems on the board here for you, and then I'm going to give you some of them to do. And then the next period, I'll do some dilution ones, and I'll give you some of them to do. Okay, copy that one down. So I'll give you the grams, and this is going to happen in a lot of the problems where you'll be given grams instead of just a molarity directly. You should know how to get the molarity from that. All right? Molarity is, and you need to write down the formulas, moles of solute per liters of solution. So you write the formula down. And then you have to realize that you don't have moles, you have grams, and you don't have liters, you have milliliters. So you have to do this like you would have done it last year. I don't know if I did, because I made this up last year, but I probably used almost the exact, if not the exact same examples for these problems when I was teaching them originally last year. 40.0 grams, I got to convert to moles. Everybody knows how to do that. Grams on the bottom, moles on the top. Salt is sodium and chlorine, 58.443, if you add them up. And that's your numerator. So you simply convert your numerator from grams to moles. Now, the second part, the denominator, is how many liters of solution you have, and that's going to be 2.000 liters. Because milliliters, I hope by now you all can convert that in your head without doing it the long way. Do that on a calculator and see what you get for your molarity. Because that's what these first questions you're going to get in the homework tonight, the first period's homework. 0.342, you said? Anybody else get 0.342 molar? Yeah. And that's how it's read. Capital M. Anybody else get that? Yeah. Molar or moles per liter. Say, I want you to realize that there's 3 ways I'm going to be able to write that down. Molar, M, capital M, small m means molality, and moles per liter. The reason I want to point out that moles per liter last one is that the very next example, you're going to see why. Watch. You kind of have to understand that's what molarity means. In this example here, this is a typical, as I've called them in the past, strawberries in baskets kind of problem. It's that easy. It doesn't even require a calculator, nor does it require you to write anything down. Now, we're going to write something down to show you how to do it, because it won't always be that easy. But that's all you're doing here is I went picking strawberries. I picked 2 baskets of strawberries, and each basket held 4 pounds. How many pounds of strawberries did I pick? I picked 8. It's exactly what you're doing here. Again, a little bit of a review from Chem 1. All right? And here's the reason it works. Because 4 molar means 4 moles per liter. So it works by common sense. 4 pounds of strawberries per basket, I pick 2 baskets. It also works by conversions. I've shown you from day 1 in Chem 1 how to do conversions because I knew how important they're going to be the rest of the year, rest of the 2 years. 2 liters. Liters cancel and leave me with 8 moles. That's how easy this problem is. All right? But it's only easy if you understand that molar means moles per liter. That's the same thing. So you have to have that in your head. Otherwise, it doesn't make any sense. All right, so that's all you do for that one. And you will have to do that sometimes. And finally, I have one more example to do before you start your problems. How many grams of oxygen gas must be dissolved in 0.500 liters to make a 0.240 molar solution? This is an example of how I can expand a problem that's as easy as the previous one and make it unrecognizable to you. This is the same problem as the one above it. I just added a little bit on, I just changed the numbers and made them a little bit uglier, but it's the same exact problem. Look at it. How is this the same problem? Well, this question gave me a molarity and it gave me a volume. This one gives me a molarity and it gives me a volume. It's the same problem. What did it do to ask me a little bit more? Well, instead of moles, at the end of this one, I ended up with moles. It asked me for grams. Well, again, because we know how to do conversions, we could convert this moles to grams. We didn't because we weren't given enough information to do it. We weren't asked to do it. We certainly are here. So let's just do this the same exact way I did the one above it. I have a 0.240 molar solution. So that's 0.240 moles per liter. They're the same thing. Moles per liter. What am I going to do with that? Well, I'm going to multiply by how many liters I have. I've got 0.500 liters. I've got half a liter. Now, I don't stop there and hit equals. I don't have to. That's the other beauty of using conversions. I can just keep going. I'm now in moles. I can just keep going. I want to know how many grams of oxygen, so I should certainly know how to do this. Moles are on the top, so moles go down the bottom down here. They have to cancel. Grams are on the top here. 1 mole contains how many grams of oxygen gas? Yeah, I got to remember something. 31. I got to remember it's diatomic. It's not 15.999. 31.998. Do the math for that. $3.84 grams. And that would be your answer. All right, I'm going to put these problems on the board. I'll write them up here, even though there's nobody asking still. Page 117. I'll write them over there later. Page 117, numbers 60 to 63, 64B, 65A, and 66, and 67.